All right, let's do an example of a precipitation reaction where we're doing quantitative analysis. So quantitative, how much? Quantity. So here's a question. This is actually really similar to a question that's in your question pack that I assigned to you. I think it's in assignment 22. So 1.00 liters of polluted water contains an unknown amount of lead 2 nitrate. A precipitation reaction was performed and 8.31 grams of lead 2 iodide precipitate were recovered. How much lead nitrate was in the original solution? So we want to know the mass. So we need to get grams of lead nitrate. So first thing I'd want to do is figure out the relationship between lead nitrate and lead iodide. So the nice thing is the coefficients, the subscripts on both of these are the same. So let's say that we were using sodium iodide. We can do a really quick and dirty kind of chemical reaction. We're starting with lead nitrate because that's what was in the original polluted water. And we're adding sodium iodide. And I can tell you right now there's going to be a 2 in front of this guy. Let's see, that's aqueous. And so is our sodium iodide. And we are going to end up with PbI2, which is solid, and NaNO3, which is aqueous. And there's a 2 that goes in front of that. So if we look at the balanced chemical equation, we have an automatic implicit 1 here, and we've got an implicit 1 here. That means our mole ratio is going to be 1 to 1. So literally what this question is asking us in a very roundabout way is how, this is just a stoichiometry question. So we measured our PbI2, so I want to know the moles of PbI2. So we have our mass. We get our conversion, and we're going to use the molar mass of PbI2. And we need to figure this out where everything goes. Remember, since we're trying to find moles, we're going from grams to moles. Moles is going to go on top, and 461.01 is going to go on the bottom. I'm just going to grab my TI calculator here. 8.31 divided by 461.01 gives me, and I'm just going to write this down. I'm going to keep the number in my calculator, but I'm not going to write all of it. So 0.018 moles of PbI2. Consider this. If we precipitated all of the lead out, remember we always want to use excess, aka extra, of whatever is causing the precipitation. Because if you just put a certain amount in and you're like, okay, we're done, what if you could have added a couple more drippies of sodium iodide and gotten a little bit more lead iodide to precipitate? You always want to add more until you stop getting precipitate, and then you add a couple more drips of whatever's causing the precipitation, in this case sodium iodide. So that means that we're going to ensure, that means that this measurement here, this 8.31, is all of the lead. We've knocked all of the lead out, which means that this number here is accurate. Now I have to throw this number through the mole ratio. Remember, the mole ratio that we care about is between lead nitrate and lead iodide. We do not care in any way about the sodium iodide and the sodium nitrate because those are spectator ions. The NaI was just there to hold on to the I minus, and NaNO3 is not what we care about. We care about the lead. So the lead compounds are what we're dealing with. So let's take a look at that. So we have 0.018, and that's moles of PbI2. We use the mole ratio. We want to cancel out PbI2. So we put it on the bottom. We're bringing in PbNO3 too. Awkward bracket. Since this is a 1-to-1 mole ratio, we're going to end up with 0.018 moles of PbI2. Oh, shoot, I mean NO3 too. Bracket NO3, bracket 2. So now we've got the moles. It's asking us what mass of lead nitrate, so I'm going to multiply by the molar mass of lead nitrate. So 0.018 mole. We're going to multiply by the molar mass, 331.2 grams per mole. So whatever number is in my calculator multiplied by 331.2 gives me 5.97 grams. So again, this question is asking us, we had a container with an unknown amount of chemical, we did a reaction, and then we recovered this much precipitate. Then we had to go backwards and say, okay, if this much precipitate we were able to make that much precipitate, how much lead nitrate, the original chemical, was there in my solution? And now we know 5.97 grams of lead nitrate was in my solution. Let's do one more, and then let's do one where the coefficients are not going to be the same. Let me just check my sol chart. Let's do, oops. Sure, let's do iron 2 chloride. Yeah, sure, let's do iron 2 chloride. So we will say, iron 2 chloride. So how much iron 2 chloride was in the original solution? Solution. Okay, so the reaction here is going to be, okay, we have iron 2 chloride, FeCl2 aqueous. We are reacting it with sodium phosphate. Now, you'd have to go to your table of ions or to your salt table. Phosphate has a charge of -3. That means that since sodiums have a charge of +1, sodium phosphate will have the formula Na3PO4. That's just reading the formula or reading the name of the chemical and getting the formula from it. So how is this going to work? Well, we're going to make NaCl. That's one of the chemicals that we're going to make. And remember, that one is spectator. We don't care about it. And the other is going to be iron 2-phosphate. Here's where it gets a little bit troublesome because phosphate ions have a charge of -3. Irons have a charge of +2. So that means that we have to balance it, which means we're going to go Fe3PO4 2. Why does that work? Because if I have 3 Fe2 pluses, that's a total charge of +6 from the irons. If I have 2 PO43 minuses, that's 2 times -3, that's -6. So this is balanced. We always make sure our ionic charges are balanced. Now we just have to balance the actual reaction now. We balanced our individual chemicals. Now we have to balance the actual amounts. So the coefficients. So I'm going to change colors here. So like a dark blue. Cool. So let's see. We have 3 sodiums and 2 chlorides. So if we're making sodium chloride, we got to have 6 of these total. So if I throw a 3 out front here, and I throw a 2 in front here, 3 times 2 is 6 chlorines. 2 times 3 is 6 sodiums. So that means my coefficient in front of the sodium is 6. Now we just make sure everything else is balanced. I have 3 Fe's, and I have 3 Fe's that are all locked up inside of this iron 2 chloride or phosphate. I have 2 PO4s here because PO4 in brackets with a little 2 means 2 PO4s. And I have 2 out front times 1 PO4, so that's 2 PO4s. So this is my balanced chemical reaction. Now we have to find the amount of moles of iron 2 phosphate. And I don't have this, I didn't pre-Google it, so I'm just going to look it up now. Iron 2 phosphate. And that has a molar mass of 357.48 grams per mole. So 357.48, and that's grams per mole. Remember, all of our work is going to be done using moles, so we got to convert to moles. And the question is asking us how much iron 2 chloride was there to begin with. So I want to find the molar mass of iron 2 chloride, which is 126.75. So 126.75. And I'm still going to write my units, grams per mole. So our job is this. We find out how many moles of iron phosphate we made. We've already got grams of iron phosphate. So there's my grams of iron phosphate. We are going to convert grams of iron phosphate to moles of iron phosphate using my molar mass, 357.48 grams per mole. We know that my answer is going to be in moles because that's like the whole point. So 17.3 divided by 357.48. Oops, I multiplied by accident. Whoops. So that's 0.0484 moles. And again, remember, I'm just writing the first couple digits. I'm keeping my number inside my calculator. In real life, it's 0.0483943158. But am I going to write all those numbers? Not a chance. So this is moles of Fe3PO4. 2. Now I've got moles of Fe3PO4. I need to use the mole ratio between the two chemicals that I care about. Remember, I don't care about the sodium containing chemicals. The sodium phosphate was there just to carry the phosphate so I could precipitate. And sodium chloride is both the Na plus and the Cl minus. Those guys are spectator ions. I don't care. So I only care about the things containing Fe. So I'm going to go in with my number of moles of Fe3PO42. So 0.0484 moles. And I'm even going to write the actual chemical formula, PO42. I get my conversion bracket, and my answer, or this part, is going to be in moles of FeCl2. Because we're going from this to this. So how do we set it up? Well, we have to have 3 FeCl2s up top from my balanced chemical reaction. That's my wanted over my given, which is 1 Fe3 PO42. So that's going to let us rid ourselves of the Fe3PO42, and it's going to bring in the FeCl2, which is what we care about. So I'm just going to multiply the number that's already in my calculator by 3, and we get 0.145 moles of FeCl2. Now that we've got moles of FeCl2, we got grams per mole, we can find out the grams. So 0.145 moles of FeCl2 multiplied by the molar mass, 126.75 grams per mole. .126.75, enter, we get 18.4 grams of FeCl2. In other words, 18.4 grams of FeCl2 is in the original sample of polluted water. We hit it with Na3PO4 to knock out all of the iron. We precipitated it, then we collected and dried the iron phosphate, and we got 17.3 grams of that. And then we were able to use that plus the balanced chemical reaction to go back and solve how many grams were in there. So I hope that helps you guys out.